Ethereum is a decentralized, transaction-based state machine. Ethereum was designed to make smart contracts more usable for developers. Smart contracts are decentralized programs that usually allow for some kind of transaction between the owner of the contract and anyone who would like to purchase something from the contract owner. For example, I could set up a smart contract where a listener sends my smart contract some Ether, and I send the listener a podcast episode automatically. Smart contracts can also interact with each other to network together complex transactions. In the same way that web development has been made easier by platform as a service and software as a service, smart contracts will make building financial systems much simpler. It's going to be a really bright future, but in the meantime, it's going to be rocky to get there because the infrastructure has a long way to go. And today's guest, Preethi Kasireddy, is no stranger to blockchains. She's a blockchain developer who writes extensively about cryptocurrencies, and she joins the show to describe how the Ethereum platform works, including the steps involved in a smart contract transaction. This episode covers some advanced topics of Ethereum. Like yesterday's episode, I was out of my comfort zone, and there's a good chance you will be too. But if you're looking to get acquainted with the more basic aspects of cryptocurrency, you can look at our back catalog. We have tackled the basics of cryptocurrencies in some of our episodes, and you can find them in the Software Engineering Daily app for iOS or Android. You can hear all of our old episodes, and they're easily organized by category, such as blockchain. And as you listen, the Software Engineering Daily app gets smarter, and it recommends you content based on the episodes that you're hearing. We've done 600 episodes, and there's a whole lot of content to find. If you don't like this episode, you will easily find something that you do like using our recommendation system. And these mobile apps are open sourced at github.com/softwareengineeringdaily. If you're looking for an open source project to hack on, we would love to get your help. We're building a new way to consume software engineering content. We have the Android app, the iOS app, a recommendation system, a web front end, and more projects coming soon. We would love to get your ideas for how you want to consume media about software engineering. And if you're interested in contributing code, of course, check out github.com/softwareengineeringdaily. You can join our Slack channel. We've got a nice little community going. There's a link on softwareengineeringdaily.com for the Slack channel. And at any time, you can send me an email, jeff@softwareengineeringdaily.com. I would love to hear from you. If you have any questions on the open source project or feedback on the podcast or suggestions for shows, I always would love to hear from you. So send me an email. And with that, let's get to this episode. The octopus, a sea creature known for its intelligence and flexibility. Octopus Deploy, a friendly deployment automation tool for deploying applications like .NET apps, Java apps, and more. Ask any developer and they'll tell you that it's never fun pushing code at 5 p.m. on a Friday and then crossing your fingers hoping for the best. We've all been there. We've all done that. And that's where Octopus Deploy comes into the picture. Octopus Deploy is a friendly deployment automation tool, taking over where your build or CI server ends. Use Octopus to promote releases on-prem or to the cloud. Octopus integrates with your existing build pipeline, TFS and VSTS, Bamboo, TeamCity, and Jenkins. It integrates with AWS, Azure, and on-prem environments. You can reliably and repeatedly deploy your .NET and Java apps and more. If you can package it, Octopus can deploy it. It's quick and easy to install, and you can just go to octopus.com to trial Octopus free for 45 days. That's octopus.com, octopus.com. Preethi Kasireddy is a blockchain developer, and she joins the show to discuss blockchains and Ethereum specifically. Preethi, welcome back to Software Engineering Daily.
Thank you, Jeff.
So you have been studying the Bitcoin and blockchain space for a while. You worked at Coinbase for a while, and then you have been writing more recently, and you've gone off on your own. So I want to get a picture for the basics of Ethereum in this episode. And I think most of the people listening to this understand what Bitcoin is. They've probably heard a little bit about Ethereum. We know that Bitcoin is decentralized money, and we've probably heard that Ethereum is decentralized compute. It's a big virtualized machine that's spread across the world. And the question that I think is confusing to some people is, we get why you need a currency in Bitcoin because it's decentralized money. That seems like a currency would be core to that idea. Why do you need a currency in the Ethereum space?
Well, I guess taking a step back, I'm not completely sure I agree with the parallel that Bitcoin is decentralized money and Ethereum is decentralized compute. Fundamentally, they both are the underlying technology for both of them is the blockchain. And Bitcoin has a blockchain, Ethereum has a blockchain. And a blockchain is just kind of the most general way to think about it is like this journal or ledger which stores transactions that are happening on the network. And in Bitcoin's case, one application of that can sit on that blockchain is decentralized money. So, of course, Bitcoin also does enable other types of applications like smart contracts and so forth. But fundamentally, Ethereum tries to go above and beyond what Bitcoin offers in a few different ways. So again, Ethereum also has a blockchain. Similar thing. It contains it's like a ledger with a series of blocks. Each block contains a certain number of transactions and so forth. The underlying difference between Ethereum and Bitcoin is that Ethereum now tries to create what you said, like a decentralized compute platform, essentially, by making the language that runs Ethereum Turing complete and has state, like it can store state. It has the ability to manage state over time. And that's how they are kind of different. And so when the main question you were asking is, why does Ethereum need a currency? Ethereum needs a currency because, again, underlying both blockchains, there's a consensus mechanism to ensure the security of the transactions, right? So like to avoid things like double spend, they both have a consensus mechanism where miners do something, like miners provide their compute power to solve a cryptographically difficult hashing algorithm, and that consensus mechanism is called proof of work. And both Bitcoin blockchain and Ethereum blockchain use the same consensus mechanism called proof of work. And the reason Ethereum has a currency is because it creates new Ethereum every time a miner provides their compute power to verify and validate these blocks. Mm-hmm. And so that's how new Ethereum is generated. And similarly, that's how Bitcoin is generated. So I guess, yeah, that's one of the main reasons for the currency.
Mm-hmm. I get it. So in Bitcoin, you've got all these financial transactions that are taking place, and they get recorded in everybody's copy of the blockchain. And the over time, the blockchains are verified by the miners who are putting their hard-earned compute into verifying those transactions. Those miners are rewarded with new Bitcoins. And in Ethereum, the thing that you're verifying, the set of transactions that you're verifying are programs. You're verifying that the same programs have been run that everybody has the same ledger of computation that has existed in the past. Is that correct?
Yeah, I mean, I think you're trying to, again, like shove Ethereum into this compute model, and I get it, but both still have, it's not programs, they're still transactions. Ethereum has the concept of transactions as well, but the difference is that in Bitcoin's case, they follow this model called a UTXO model. So for every transaction, it's essentially a set of input UTXOs, which are unspent transactions, and then it's a set of outputs that spend that transaction. So it's basically a ledger that kind of keeps track of transactions moving from one account to another, and all the unspent ones then become spent. Then those become unspent when they go to the next sender and so forth. With Ethereum, they still have the concept of transactions, except the difference is that these transactions are allowed to interact with code, because Ethereum has this concept like unlike Bitcoin, which has one type of account, Ethereum has two types of accounts. One is called like an externally owned account, and you can think of this as like a user account. And this is an account that you would have, for example, to maintain your own Ether balance, any kind of wallet that you own, like that would be associated with an externally owned account. These accounts live outside of Ethereum's ecosystem. And then you have a contract account, and a contract account has code associated with it. So a transaction has the ability to execute code on a contract account. And that's the kind of fundamental difference between how transactions work in Ethereum versus Bitcoin.
So in a contract account and an external account, you both have, in both situations, you have some Ether sitting there. And then the external account is more like just your external wallet or your store of value area. And then the contract account is this repository for, it's like code together with Ether, so that that code can execute in transactions involving Ether. Is that right?
Not necessarily. Like the contract account doesn't actually have to have any Ether, and neither does, you can have a zero balance on a contract, right? It's just that when a transaction occurs, it's like you can think of a contract as this like autonomous object that exists in the Ethereum ecosystem. And every time you send a transaction from an externally owned account to a contract, it's like poking that contract and say, hey, run this function. And that function might transfer Ether to another contract or to another account, but it can do so much more than that. It can store something in the world state. It can do calculations. It can do for loops. It can do a lot more than just send Ether back and forth across accounts.
Okay. Well, let's just go ahead and dive into the idea of a transaction, because this is a deep subject. Why don't you define that term transaction a little more holistically for us?
Yeah. Again, so transaction, you can think of a transaction as basically this like assigned piece of data or assigned like data package, and it stores the message that needs to be sent from the externally owned account to either another externally owned account or a contract. And this transaction will contain a few different things. The main things are like obviously the recipient of the message. It'll contain the signature that like actually identifies the sender to verify that the sender is a valid sender. It'll contain, if there's an amount of Ether that the sender wants to transfer, it'll contain that amount value. It also has the ability to contain extra data. So like this, let's say you're an externally owned account is sending a transaction to a contract and it wants to input some data into that contract. It can also send data along with it. And two other things that it contains that are very important are something called a start gas value. And this kind of represents, you can think of this as like the gas limit, which is basically like how much is the sender willing to pay to execute this transaction? How many computational steps are they willing to take and pay to execute this transaction? And they set a limit on that. And then the other thing it contains is called like a gas price, which is like a representation of how much the sender is willing to pay per step. And this is kind of what composes a transaction. And yeah, again, the transaction can then be sent to either another account or a contract, and it gets executed.
Can you give us an example of a contract? And walk us through the transaction steps?
Yeah, sure. So let me see. That's a good example. Yeah, let's say I have a contract that has just one function and it accepts some piece of data and it stores it in storage, right? Mm-hmm. So what happens is I'll send a transaction and it'll contain all the fields that I just said, which is the recipient, the signature that identifies that you're the sender, some Ether amount if you want to send it, some data field. So in this case, data field would be what data you want to store. And then the start gas or the gas limit value, and then the gas price. So that you send that transaction across. And first what happens is we first check if the transaction is well formed, like it has all the fields that it needs to have. And then what's done is like we calculate the transaction fee. So this is calculated by taking that start gas amount that you provided times the gas fee. Because again, in the start gas, you stated how many computational steps you're willing to provide. What is the maximum number of computational steps you're willing to take? And then the gas price is how much you're willing to pay per per step. And so you just calculate what the transaction fee is by multiplying those two. And then that amount you subtract from the sender's account balance. And then once you subtract that balance, you increment something called a value called nonce on the sender's account. And the nonce is basically keeping track of how many transactions the sender has actually sent over time. The reason we do this is to avoid double spend. So we can't do like replay attacks where the sender tries to do the same transaction twice. The nonce keeps track of that. Once those two steps are done, then we initialize gas to the start gas. So far we've spent the start gas times gas price amount. And what happens at that point is then the data is sent to the contract. And to store that data, perhaps it costs X amount. So we again subtract that amount of gas from the total amount that you're willing to pay, and we keep subtracting for each computational step that you take from that total gas that you're willing to pay until either the transaction fails or it succeeds. It can fail for various reasons. For example, one reason it might fail is that it runs out of gas. You didn't provide enough gas for all the computational steps to run on that contract to store that piece of data. And then in that case, it'll fail. So what will happen in the failure case is the gas will still be paid for. Like you won't get your gas back, but if you sent any Ether along with it, that will be refunded to you. And then if it succeeds, if the transaction succeeds, then that gas gets paid to the miner. And any gas that you didn't spend based on the maximum amount that you provided will get refunded back to you. And then the state will move to the next state based on what you stored in storage.
Every second your cloud servers are running, they are costing you money. Stop paying for idle cloud instances and VMs. Control the cost of your cloud with Park My Cloud. Park My Cloud automatically turns off cloud resources when you don't need them. Whether you're on AWS, Azure, or Google Cloud, it's easy to start saving money with Park My Cloud. You sign up for Park My Cloud, you connect to your cloud provider, and Park My Cloud gives you a dashboard of all your resources, including their costs. From the dashboard, you can automatically schedule when your different cloud instances get turned on or off, saving you 65% or more. Additionally, you can manage databases, auto-scaling groups, and you can set up logical groups of servers to turn off during nights and weekends when you don't need them. And you can see how much money you are saving. Go to parkmycloud.com/SEDaily to get $100 in free credit for Park My Cloud for SE Daily listeners. Park My Cloud is used by corporations like McDonald's, Capital One, and Fox, and it saves customers tens of thousands of dollars every month. Go to parkmycloud.com/SEDaily and cut the cost of your cloud today. That's parkmycloud.com/SEDaily. Okay, so that's a really, really descriptive example of how an Ethereum transaction works. And because there's so much detail there, I think I want to revisit this a third time. I've done some shows about Ethereum, but I have not gone into this level of detail. And so I want to present you gave a really good exemplification, but I want to get an even more concrete example. So what I'm thinking is something that's like an actual application where people could use this. And one example I'm thinking of, if you can tell me if this is a bad example, and we can discuss something else. But one example I'm thinking is, let's say I want my Software Engineering Daily podcast contract, where basically the user can send some amount of Ether, and I'm going to send them back a MP3 to a podcast episode, or maybe they can also send me a different amount of Ether, and then they subscribe to the podcast, and that means I'm just going to push MP3s to them all the time. I'm going to store their user data so that I'm learning about what episodes they listen to. Would that be an interesting example to explore, or should we do something more traditional, like, a mortgage-backed security or something like that?
That's fine. It'll be the same explanation again, so I'm happy to repeat it. Let's take the example of you're trying to have a contract that builds a subscriber list, let's say. And I'm gonna keep it simple. I'm not gonna do the second part where you said I send back stuff to the contract, because then it gets into a whole new ballpark, because then you're doing contract to contract calls, and that's adds an additional layer of complexity. So let's say it's just one way, right? Like an externally owned account is trying to say, okay, register me for your subscription list. So you have in your contract, you're storing some list of addresses that represent who is subscribing to your list. So this externally owned account would, I guess I'll put it from a end user perspective, how they would send this transaction in. So you would log into some software, whether it's My Ether wallet or MetaMask or some kind of wallet that allows you to send transactions to Ethereum contracts. And then you say, all right, you get the contract address and you say, here's who I'm sending it to. Here's how much Ether I'm sending with it, if you decide to send any kind of Ether with it. Here's the data. Here's some data I send with it. Maybe the data might be like you ask for, I don't know, their age or their birthday or their credit card number. I don't know, whatever it is. Like you might ask for some data fields when they subscribe, so they might want to send some data along with it. And then they go ahead and they hit send. And then the client software will say, all right, how much gas are you willing to spend on this? And then the user can state how much gas they're willing to spend. And then at that point, they can hit send. And that transaction will be sent to your contract. Your contract will then execute that function, and it'll say, all right, to store this, and then Ethereum has a calculation to determine, all right, to store this is how much it's going to cost. So Ethereum will calculate that, and every time you do some kind of computation in the contract, it'll calculate the gas and deduct it from the maximum gas limit that the user is willing to spend. And then it'll keep doing that until it finishes. In this case, you're just storing the user's address in some array, let's say, so that you'll store that in your storage. The Ethereum will calculate how much gas you used for that, deduct it from the gas that the user is willing to spend. Anything that the user didn't spend will be refunded to them into their account. And then now you have a list of people who are just sent. Now you have an updated list of addresses with the new subscriber, and then the miner will get the gas fee that was charged for doing that computation.
And that computation gets logged on everybody's blockchain eventually.
Basically.
We should go into that. Like, so we'll take a step back and say, so if I'm the customer, I've stated my gas amount that I'm willing to spend in order to subscribe to this thing, and if the network has enough liquidity, then my gas price is the gas that I'm willing to pay is going to meet the liquidity amount in the network, and my transaction is going to go through, and the contract is going to execute. It's going to get, I'm going to get back anything that I'm supposed to get back, or anyway, the contract is going to, I'm wording this worse than you could, so I'll stop rambling. The contract is going to execute, and then the execution is going to get logged in the blockchain somehow, and then it's going to get shared with everybody else's copy of the ledger. Let's just go into that. Explain how that verification happens, how the ledger is getting shared with everybody else.
Yeah, sure. So I guess the best way to think about this is the best way to explain this is to understand how blocks on Ethereum how transactions get validated is through this block validation algorithm, meaning like every block has a set number that holds a set number of transactions, right? And so every time you want to validate the state of Ethereum, you have to validate the blocks. And to validate the blocks, it's like this entire process where you have to check that the previous block is valid, and then you check that the timestamp is valid. You check all these different parameters, and then what you do is basically you take all the transactions that are in that current block, and then you apply them, and then you check that once you apply them, the end state of that block matches the end state that you expected. So there's this block validation algorithm, and basically, like, I think the question that you're trying to ask is like, where is this contract code executed? Like, how does that actually work? And the answer is like, the process of actually executing that contract code is actually the definition of the state transition function itself, which is part of the block validation algorithm. So if a transaction gets added to some block, then the code that's executed by that transaction will be executed by all the nodes, like from now and into the future. Anyone that tries to validate that block will have to execute that transaction as a result of validating the block.
They have to execute the entire thing. Isn't there? So there's no thing where like a preponderance of them executes it, and then it gets like rolled into a Merkle tree, and then the verification in the future is easier. You literally have to run all of the transactions.
Nope. The code execution, like that's run by that transaction, will be executed by all the nodes that download and try to validate any block. So the purpose of the Merkle tree is that it efficiently stores all state that exists in Ethereum. So it's an efficient way of storing past state, and then whenever state gets updated, the Patricia Merkle tree is what Ethereum uses. It just has to update part of the state that got updated, and it references that state, but that doesn't mean that the blocks are not getting validated each time. The state is not necessarily being recreated each time, but the blocks are being validated.
So let's say Ethereum's been running for a really long time, and I want to join the Ethereum network with a new node. Do I need to run all of the past transactions, or can I just take the Merkle tree at T0 and that's...
So yeah, there's basically, to run the full chain, if you're a miner, you definitely have to. You're going to want the full node. So you're going to have to start from the Genesis block. For example, for me to sync the blockchain, when I first got started with Ethereum, it took about a day and a half for me to sync the full node. And I have like a brand new 1 terabyte Mac laptop. And so yeah, you have to basically run the entire chain. But of course, Ethereum now offers light clients, and this is where they kind of prune certain parts of the state that you don't need to revalidate over and over and over again. And they let you start from basically a simpler state. And that way, like the lighter clients took me like about less than an hour for sure to sync the whole thing, which is like not bad at all. But again, like that's what I'm saying. You have to revalidate at least some part of the state. And so there's the options to do lighter clients versus full nodes. I think you're confusing the Merkle tree. Merkle tree is more to manage the state. It's not necessarily the validation of that state.
Well, right. But what I was saying was like, if you join the Ethereum world as a new node and everybody has an agreed upon state of the present day, why would you need to rerun all of the past transactions? Because shouldn't there be no difference between the state that you would observe after running all of the...
Well, that's the purpose that's why Bitcoin and Ethereum are so secure, right? Every single node is verifying every single transaction.
Right, but if there's 100 nodes in the network and I want to be node 101...
that's the purpose. It's like every node adds an extra layer of security to the fact that it's harder and harder and harder to manipulate the chain. And because every single node is validating all the transactions. Every single full node, I'll correct myself, every single full node is validating every transaction. Of course, again, like I said, there's light clients and so forth, so they're not validating every transaction, but every full node is.
Sure. What I'm still confused about is if all the 100 nodes before I join the network have validated everything in the past, and they all agree on the state of the Ethereum blockchain, and they all agree that the transactions on the transaction chain that has occurred up until T0 when I'm joining, and they have a Merkle tree that represents the current state of affairs, why can't I just copy the Merkle tree and then copy all subsequent transactions, and then I process all subsequent transactions?
Again, this is what light clients let you do. It is possible, but for a full node, you have to execute all the transactions. And of course, as a developer right now, I'm using a light client just because I don't want to have that burden. Like if I had to download the full chain on Ethereum, I think it's like over 10 gigabytes right now. And whereas like the light client, I can only download, it's like between 2 and 4 gigabytes. So it's much lighter and I don't have to process every transaction.
And let's go just a little bit deeper into the way that a transaction gets validated. So I get that the Merkle tree represents the state right now that everybody agrees upon. Well, not necessarily. If we all have the same Merkle tree, then we all agree on it. But the Merkle tree is a representation of state. And Merkle trees, by the way, for people who don't know, are just this it's like a tree of hashes. It's like if you know the data structure a trie, it's just an efficient compression mechanism for, it's like how Git repositories are managed. You can look into the past with a Merkle tree, and but it's a compressed data structure. So what I'm curious about, and you probably have said this like 3 times already, but I'm just going to ask you again because I still don't get it. This transaction occurs, and a user sends Ether in exchange for a contract executing. The Ether that they send is an amount that they're willing to pay, their gas limit, and the gas limit is associated with the amount of liquidity in the network, and then that transaction. Can
you explain what you mean by liquidity in the network?
Oh, sorry. Yeah, I'm probably misappropriating terms, but by liquidity in the network, I mean the gas. Like you state your gas limit, and the gas that actually gets used, the Ether that actually gets used to pay for your transaction executing across the network, is based on how many nodes are active in the network, right? Like if there's more nodes in the network, then it's going to take less gas to spend. Actually, I could be totally wrong about that.
No, not at all. Gas is, again, simply just Ethereum has in its white paper, in its yellow paper, it strictly defines how much gas each computation step costs.
Oh, okay.
Regardless of which node.
Oh, okay.
Yeah.
Interesting.
But of course, there's a gas price you can set, which determines how much you're willing to pay per step.
Oh,
but
okay.
So the gas price and the gas limit are different. Gas limit is like how much in total gas are you willing to spend, and then the gas price is basically like per computation step, what's the per unit gas.
Okay. Well, then actually, okay, then let's go deeper on that gas stuff. So you said the price. So much to unpack here. So the gas price is set for each computation step. What are you talking about there? Can you explain that a little bit more? Yeah,
sure. I know this can get kind of confusing. So gas price is basically the fee that the spender is willing to pay per computation step. So, and Ethereum has like for example, I'm looking at the yellow paper right now, let's say if someone wants to get the balance in a contract, the value of cost is 400 gas.
Okay.
And the user determines the gas price is basically representing the fee that for every computational step. I guess I'm not doing it. It's like confusing trying to describe it, but
I hear you. So it sounds like there are primitives in Ethereum in the language of Ethereum transactions. There are primitives that have set prices, but I guess I'm not understanding why. Okay, so there's primitives that are set. Is that right? Or
yeah. So I guess the fundamental unit you can think of for every computation, the fundamental unit is gas, and usually most steps cost let's say 1 gas. But some more heavier operations will cost more gas because they're just more computationally expensive. I think that's the best abstract. That's the best way to kind of think about it at a high level. And then to store, for example, to store something, it costs more gas than to add 2 values together. Just because storage is much more computationally heavy on the entire state of the network than adding 2 operations. And so that's kind of what gas represents. And then the user just determines how much they're willing to spend on gas to execute that transaction.
Why do they have to set that number? Because if I have a contract and you want to execute that contract, it seems like the contract price would be set based on the operations that I'm running in my contract. Aren't you just paying the price that's set based on that?
Yeah, that's a great question because a lot of these clients do is they offer the user, hey, here's the recommended amount of gas to spend, and usually it's like 21,000 gas. But the reason the user has the ability to set more is because some things just cost more gas. For example, sending a simple transaction, like for example transferring Ether from one account to another, is much less gas than creating a contract, for example. And so you want the ability to increment how much gas you're willing. You want to be able to spend more gas on transactions that just require more gas. And then second reason is because it's also a protection mechanism, right? Because let's say because Ethereum is Turing complete, it allows for loops. And so there's a possibility that some of these contract calls or some of these function calls can go into literally infinite loops, or just there might be malicious attackers who are trying to create contracts that just go through ridiculous numbers of computational steps. In that case, as a miner, if you see that some attacker puts 17 million gas in a transaction, it's pretty easy to spot that, hey, this person is probably trying to do something where they're trying to do something that either goes into infinite loop or just do an incredible number of computational tasks. So it kind of gives that visibility into that.
Who do you use for log management? I want to tell you about Scalar, the first purpose-built log management tool on the market. Most tools on the market utilize text indexing search, and this is great for indexing a book, for example. But if you want to search logs at scale, fast, it breaks down. Scalar built their own database from scratch, and the system is fast. Most of the searches take less than a second. In fact, 99% of the queries execute in less than a second. That's why companies like OkCupid and Giphy and Career Builder use Scalar to build their log management systems. You can try it today, free, for 90 days if you go to the promo URL, which is softwareengineeringdaily.com/scalar, SCALYR. That's softwareengineeringdaily.com/scalar. Scalar was built by one of the founders of Writely, which is the company that became Google Docs. And if you know anything about Google Docs history, it was quite transformational when the product came out. This was a consumer-grade UI product that solved many distributed systems problems and had great scalability, which is why it turned into Google Docs. And so the founder of Writely is now turning his focus to log management. And it has the consumer-grade UI. It has the scalability that you would expect from somebody who built Google Docs. And you can use Scalar to monitor key metrics. You can use it to trigger alerts. It's got integration with PagerDuty. And it's really easy to use. It's really lightning fast. And you can get a free 90-day trial by signing up at softwareengineeringdaily.com/SCALYR. softwareengineeringdaily.com/scalar. And I really recommend trying it out. I've heard from multiple companies on the show that they use Scalar, and it's been a real differentiator for them. So check out Scalar, and thanks to Scalar for being a new sponsor of Software Engineering Daily. So when I make my contract, I'm sometimes saying there is some non-determinism from the person who's going to call that contract. It's not like the contract is going to have some fixed price. There might be there's some variability, and that's why you want to set the amount that you're willing to spend.
Yeah, and also let's say it can be accidental too, right? Maybe you accidentally start an infinite loop. You want to be able to set the max limit of gas that you're willing to spend as a sender on that transaction, so that your infinite loop doesn't spend all your ether, right? So there's a lot of protection mechanisms here too for why you want to set that gas.
So if I set a gas limit and the contract tries to execute for more than the gas limit, do I lose the amount of money up to that gas limit? If the thing doesn't fully execute?
Yeah. So what happens is you do lose the fee, you lose the gas amount, but let's say you were trying to send me 5 ether, but you didn't put enough gas. You'll lose the gas, but you won't lose the ether. The ether will be sent back to you. So that part of the state transition will be rolled back, but the fee won't be rolled back because Ethereum did spend X amount of computational power to run that transaction until it ran out of gas, right?
Okay, interesting. Getting back to our example of I pay to subscribe to something. I call this contract to subscribe to something. I pay some amount of gas. I may be paying Ether to get on that subscription list as well. So I've sent gas and Ether. Am I correct there so far?
Yeah.
Okay. So sent gas and Ether along with some arguments that state, maybe who I am and how I want to subscribe to this thing, other metadata, and the person who's running the contract, the subscriber list, they are going to execute their contract across my arguments. Is there anything interesting there we should discuss? Like, I guess the execution, the code execution is written in Solidity. Is that correct?
It can be written in. There's a few different client side or like higher level language. So the base, all contract code is written in something called EVM code, which is like Ethereum virtual machine code. But obviously, no one wants to write in a stack-based language, and so Ethereum has a few higher level languages. Solidity is one of them. It is probably the most popular and most well-maintained one. And then it also has others like Serpent, and Serpent is more closer to Python. Solidity is closer to JavaScript in terms of how it looks and feels. And then they also have something called LLL. And then I think Vitalik is working on a new language called Viper. It seems like Vitalik loves writing new languages. So there's a few different ones, but basically the main one you should know about is Solidity because that's what most of the industry seems to be standardizing on.
Okay, so my contract is written in something and it is going to execute. And is the first execution of that contract just taking place on the contract that the node that is hosting that contract?
I guess, what do you mean?
So
no single node necessarily hosts the contract, right? Again, like all the transactions occur. It goes back to this block validation thing that I talked about. A block has the X number of transactions. Those transactions execute code, and that's how code gets executed.
Okay, so when I am sending when I have stated that I want to send this subscription request, I want to subscribe to this newsletter or something, and I'm paying for it. Where am I sending it? What node am I sending it to? I'm sending it to any node?
You're not sending it to a node, right? So again, going back to our concept of accounts, we talked about how we have externally owned accounts and contract accounts. Those contract accounts have code associated with them. And that's where the code lives, right? And every time you want to execute code, you send a transaction, and that transaction gets executed as part of the state transition algorithm. Every time a state needs to transition, it'll execute that code.
Does that mean that I have a copy of the smart contract that I'm sending it to? If I have a node, then I can just execute that contract basically on my own node, and then it propagates to other nodes?
So you can think of the world state of Ethereum blockchains are replicated databases, right? So your node won't be any different than any other node in the network. So it's not like your contract only exists on your node and it doesn't exist on every other node. Every node is the same. And you can think of this, so the world state of every node has the entire state of Ethereum, right? And so you can think of the entire state as you can think of it as a state is basically the set of accounts. It's like an address and an account. And there's two types of accounts. There's the externally owned account and the contract accounts. The contract accounts have code with them. So regardless of who created the account, how you send a transaction is you create a transaction, you send it, and that gets broadcasted to the network, and then those transactions get executed by all the nodes.
Okay, so the first one is probably going to execute on my node, though, right? Like, does that transaction? I guess it needs to propagate to all the other nodes regardless of how successful it is, because I'm going to pay some cost to it regardless, and that cost paid has to propagate. So regardless of what happens during that transaction, whether it's successful or failure, the record of that transaction attempt is going to propagate to all of their nodes.
Yeah. That's right.
Okay. So you've got the contract on your node, the smart contract that you're going to execute against. You're going to send your transaction. You're gonna call that smart contract using your internal Ethereum account to pay for it, and then I guess okay, and then
it gets broadcast to the network, and basically how it gets broadcasted is just off the internet, and then every node that's listening for transactions can hear that transaction being broadcast, and yeah, that's how it gets broadcast to the entire network, just off the internet.
Does that happen instantly, or does it happen after does the transaction have a serialized, it executes fully and then it gets broadcast, or when does it get broadcast?
So it gets broadcast, but that doesn't mean it got verified right away. So there's a time difference between between the time you broadcast your transaction out and the time that someone actually validates that transaction. And the only time your Ether is, everything is like, the only time the state changes and updates is once your transaction is actually validated by some miner. Some mining, yeah.
Okay, so it gets broadcast, and then it finishes running, and then there's the verification or something. I guess walk me through this in a little more granular detail. Like I'm trying to understand the series of events in which this transaction gets executed, and then it gets initially executed, and then if it's successful or failure, like what happens, and then when it gets fully verified by the rest of the network. Can you help fill the blanks in there?
Yeah, sure. So again, it gets broadcast, and every network can hear that transaction. Miners who are willing to validate that transaction can put it into their block and execute that transaction and validate it. And if they are the winning block if they're the first one to create the block and that block gets confirmed, then that transaction is validated and that transaction is now permanent.
And so you have to explicitly say you're a miner on the Ethereum network to be one of the people who is doing the mining. So the other nodes are just like hanging out, waiting for the miners to all come to a consensus on the most recent set of transactions?
Yeah, that's high level. Yeah, you can think about it that way. You have to explicitly be a mining node if you want to be a miner.
So let's see. Can you talk more about the process? And I think this is probably agnostic of whether it's Ethereum or Bitcoin, but can you talk a little bit more about how the miners come to a consensus? Because I get that they're all competing to solve some kind of mathematical equation that gets us to verification. Just talk a little bit more about how the miners come to a consensus when they have, every miner has been broadcast this set of transactions that is trying to say, hey, these are transactions that actually occurred on the network. How do they come to that consensus?
Yeah, so I can explain to you, let's say a simple example is proof of work in Bitcoin. And so proof of work is the consensus algorithm. And essentially what happens is the miners need to solve a computationally, they need to hash the block header such that the value is less than something called the nonce of that block. And the nonce is set so that the biggest thing to know here is that to solve that hash, to get to that nonce that's less than that amount, is really, really, really difficult. And there's a very tiny chance that it happens. And so you need to run this computation you need to run this hash randomly many times before you're lucky enough to hit that number and be considered the valid, or the block reward, the person who gets rewarded for running that transaction.
Okay.
And the other thing to understand also is that how difficult it is to create that hash and verify. Basically create that hash gets adjusted. At least in Bitcoin's case, it gets adjusted so that blocks only get created every 10 minutes. And if blocks start to get confirmed sooner, the difficulty gets adjusted so that blocks get verified every 10 minutes.
Okay. let's go back to the contract example. Okay, give us a more complex example. So you said that my original proposition of the users like subscribing to a podcast type of program where they're getting sent back something, you said that was too complicated. So can you ratchet up the complexity of the contract example that we've been working with, where instead of me just sending my request to the contract and the contract fulfilling that request, there's a little more interactivity?
Okay, so we talked about transactions, and we said transactions have, they're sent from some externally owned account to either another account or a contract. And let's say now you get that subscriber list, and now you want to call another contract that you own, and it does something else. And for a contract to communicate with another contract, it would send a message. So transactions are when externally owned accounts send messages to contracts, and then messages are when contracts communicate with other contracts. And it's just, you can think of messages as the same thing as the same thing as transactions. The only difference is that it's basically like a sub execution of the original transaction, right? And the difference is that it's all within the Ethereum environment. It's not coming from an externally owned account. It's not coming from the external world. So messages only propagate between contracts. And then again, it's the same thing as the transaction, and it would call the method on the other contract, do the same thing with the gas. It costs a certain amount of gas to execute every computational step, and so forth. And the difference now is that when you sent that original when that subscriber sent that original transaction to the first contract, they set a gas limit. Remember, so that gas limit has to be enough to now also execute the sub executions to other contracts that he was trying to do. So if he tried to call, like, if the first contract ends up making like 4 other contract calls or something, that an original gas limit should be enough to execute all of them. Otherwise, wherever it'll fail somewhere along the way. So that's the only other part to it. It's like, you can think of like, it's not any more complex. It's just that it's a little bit different in terms of the fact that one is a transaction, and then when contracts communicate with other contracts, they're messages.
Mm-hmm. Okay. So I want to begin drawing to a close because we're almost near the end of your time. And as you said before the show, the amount of questions I had was way more voluminous than I expected. So I don't know, maybe we'll do another show about advanced Ethereum concepts. But since we're,
I think like a more interesting topic would be like more like higher level applications or so forth, or if you have any questions about that.
Yeah, well, so you have written a couple articles about blockchain stuff. One was this really comprehensive explanation for Bitcoin and the Ethereum basics, and I used that article to create a lot of the material that we've been discussing. The next article that you wrote was about the blockchain scalability, and I think we'll hopefully do a show in the future about the scalability issues of blockchain and Bitcoin and Ethereum. Let's just like tease at that, because we've described this really beautiful system of Ethereum throughout this show. Why is it not like the fantastic solution to everything yet? What are the scalability issues that you can tease at, given what we've discussed so far?
Yeah, I mean, like you were, when we were going through the whole processing and validating transactions, you were confused of why every node needs to process every transaction, and I kind of responded with the fact that that's a security feature of Bitcoin and Ethereum, right? But again, the downfall of that is both Bitcoin and Ethereum suffer from the flaw that every transaction does need to be processed by every full node in the network, which means it's hard to scale, because as the size of the network grows, so I told you that Ethereum's chain is like, on my laptop was about like 10 gigabytes or something, and it's going to continue to grow. And there's only the number of computers that can actually manage that kind of chain is just going to get smaller and smaller. And so you start to like risk centralization. Like only a few nodes can actually start validating these transactions, and then it becomes like a tragedy where like only the big mining pools can actually validate, instead of like it being a truly decentralized network. So there's scaling challenges, and the that's kind of why Bitcoin has had this like 2 year debate in the ecosystem and communities kind of disagreeing about how to solve the scalability issue. And, they had two different sides to it. One side wanted to just increase the block size itself so that it can fit more transactions per block. So Bitcoin had the 1 megabyte block limit, and they want to increase it to 2 megabytes to just fit more transactions per block. The other side wanted to do something called SegWit, which basically moves the signature part of the transaction to a different part of the transaction, so that it does, because the signature part just takes a lot of room, but it's only really needed at one time, which is to validate the transaction, but it's not really needed otherwise. So they figured out a solution to basically move that to a different part of the transaction and lower the amount of bytes that each transaction actually eats up. And so these are kind of scalability solutions that Bitcoin has been coming up with, and they are they're already in the process of kind of implementing those. Ethereum, on the other hand, also has the same scalability challenges, and there's various solutions to these things. Like Lightning networks are one that actually started in Ethereum, and then now that started in Bitcoin and now also being implemented in Ethereum. There's something called Sharding, where you can basically, instead of every node processing every transaction, you actually can shard it so that nodes only process a certain number of transactions that they care about. There's other various mechanisms like TrueBit, which is trying to do off-chain computations. Yeah, and a few other that are kind of outlined in that post. But it's a very interesting problem, obviously, and a very real problem. And for blockchain to kind of reach the scale that we wanted to reach, and to really be able to host all the types of applications that we dream of or imagine of, we'll have to definitely solve the scalability challenges. But I'm not concerned that it won't be solved, because there's already all these kinds of solutions being researched or being implemented in the currently, and things like even IOTA, which are pretty interesting. But I think we should definitely have a conversation about that in another
Okay, Preethi. Well, it's been great talking about the Ethereum basics, and we will talk about more advanced topics in the future.
Awesome.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/sedaily. That's symphono.com/sedaily. Thanks to Symphono for being a sponsor of Software Engineering Daily for almost a year now. Your continued support allows us to deliver content to the listeners on a regular basis.
Wow!